All right, so impulse means the total change in momentum during this collision or during some movement, okay? It could be a change in momentum due to a change in direction or due to something coming to a stop. It doesn't necessarily have to be a collision. That's just typically what we think of it as, okay? So anytime there's a change in momentum, it's called impulse, and that's the equation that we use for that, okay? So change in momentum is delta P. F in this case is force, and delta T is going to be our change in time. When we're talking about impulse or the change in momentum, it goes with each of those bodies in a collision. So you can find the change in momentum for both objects or the same or one single object if it's just a change in direction or a change in speed. If something comes to a stop, you can find the change in momentum. If something speeds up, you can find the change in momentum, or during a collision. Okay, so this equation that you see will apply to each object. You can find the change in momentum of both objects. Okay. When we're looking at impulse, we typically do it in a pretty short amount of time. So anywhere from a couple seconds to a fraction of a second can be our impulse, because typically momentum changes at a pretty quick rate. All right, so if something comes to a stop or speeds up, we're not looking at a 10-minute interval here for our change in momentum. We're usually looking at pretty small time intervals, okay, a few seconds to a fraction of a second. What we're going to do now is combine our equations for momentum and for this change in momentum. So we know our original equation for momentum was P equals m times v, okay, momentum equals mass times velocity. Now this, putting a delta in front of it just means our change in, okay, or final minus initial. So when we look at this, we're looking at the change in momentum is mass times the change in velocity, okay, or final velocity minus initial velocity. What we're doing in the second equation is just taking both of these terms, which are set equal to delta P, and we're going to set them equal to each other, okay? Since we know mass times delta V equals change in velocity, and we know that force times delta T equals change in momentum, we can set them equal to each other. Yeah, this equation at the bottom, it doesn't necessarily even have anything to do with the change in momentum. It might not even ask for that, but it might ask for a force if you're given a mass and a velocity and a time. Okay, so you've got to make sure that we can plug all those three things in and solve for our next variable. All right? Do we have what we need from this screen? Okay. So this says, what's the force needed to bring a 75 kilogram object at 44 meters per second north to a stop in 2.1 seconds? So go ahead and get it written down and we'll start working through it together. So let's go ahead and start compiling our list here of what we know. All right, we know that our mass is 75 kilograms. We know that this, what's this value right here telling us? It's telling us velocity initial or velocity final? Initial, because it's coming to a stop. So that means velocity final will be what? 0. Okay, so velocity final equals 0. And when it's telling us it's going north, does that mean it's going to be a positive velocity or a negative velocity? Positive, okay, because we usually think of north and east being our positive directions and south and west being our negative directions. Okay? And then we know one other thing, and that's time. So we can use our expanded equation here for impulse, or our combined equation for impulse, which is force times delta T equals m times delta V. And we can solve here for our force. Okay, nowhere in this question does it ask for impulse or ask for a change in momentum, yet we can use that equation, okay, because it puts all of those factors into one equation. So we're going to solve for our force. We know that our time is 2.1. Our mass is 75. And this delta V means final minus initial. So we're going to have to take what minus what?
0 minus 44.
Yeah, very good. 0 minus 44. Okay, so that means it's going to be 2.1 times our force equals 75 times negative 44. Okay, which means 2.1 F equals, I think this is what, negative 3,300? Okay. All right, so to solve for our force, we then divide by our 2.1. And that means the force that's required is
-1 1,571.
Good. And what's our units for force?
Newton.
Newtons. Good. What's the negative tell us right here?
That it's stopping, slowing me down.
Exactly. That it's going south. Okay, so the force that needs to be applied must be going south. It could be a frictional force that's opposing it. Whatever it needs to be, it's in the opposite direction of this original velocity. Okay, so that's what the negative is telling us. Since our original velocity is positive, the force required to stop it must be opposing that, which means it needs to be negative. Okay, are we clear? All right, let's try another one. What's the change in momentum of an object that's acted on by a 64 Newton force for 3 seconds? It's only giving us two things here, two variables here. We know that our force, okay, well we know what we're looking for. We know that our force is 64 newtons. And we know that our time is 3 seconds. Okay, most often they're going to give you the whole delta t, okay, the change in time. We're not going to have to find delta t. They're usually going to give it to us. So whatever time is given to us, just plug it in as delta t. All right? So here we're going to find change in momentum, so we want to find delta p equals force times delta t. So this one is simple. And we get 192. What would our units be then for change in momentum? Yep. Kilograms times meters per second, just per second. Or in this case, since we took force times time, we could call them Newton seconds. You can do it either way. So it could be Newton seconds or kilogram meters per second. We're looking for just the exact momentum. We're looking for only momentum. But this problem is going to require us to use our kinematics equations a little bit. Okay, so read through it, kind of wrap your brain around what it's asking, and then we'll have to pull out our kinematics equations to solve for our velocity here. Okay, so what's going on with this object is that it starts up at a distance of 8.4 meters. It falls for a distance of 3 meters. And it ends up somewhere below that 3 meters. So that means this distance final location would be 5.4 meters. Do we agree? Okay, it falls a total of 3 meters. So if it started at a height of 8.4 meters and it falls 3 meters, it ends up 5.4 meters above the ground. Okay, are we clear with that so far? So this 8.4 would be like our distance initial. Our 5.4 would be like our distance final. Okay, we are given in our problem, we're given the mass. And that's it. All we want to solve for is momentum, but we don't have the velocity to do that. We have to figure out a way to solve for velocity first. Okay, so take a look at your kinematics equations. Think which of those equations I gave you could we use to solve here for final velocity? Okay, so if we don't have time either, so we've got to find one of the kinematics equations that doesn't have time. Yep, good. Vf squared Vi squared
plus 2a df minus di.
Good. 2a df minus di. Do we know initial velocity?
Yeah.
Yeah, when it's a dropped object, that means our initial velocity is 0. So we're going to solve for Vf squared because we want to know where it is along this path. This is considered its final velocity. Okay? So this is going to be 0. What's our acceleration when we deal with free falling?
9.8.
Yeah, good. Negative 9.8. And our distance final minus distance initial. So our final distance is 5.4. Our initial is 8.4. Okay, in this section of this problem right here, we could have just taken and put in a minus 3. Because if we chose this to be our origin, we know it lands 3 meters below where it started. We could just plug in a negative 3 there. It's going to give us the same exact answer. Okay, so we'll take Vf squared equals negative 19.6 times negative 3. And I think that comes out to be, okay, 58.8 equals Vf squared. Okay. So then to solve for our velocity, we're going to square root that. 7.7 meters per second. Is this velocity going in the up direction or the down direction?
Down.
It's falling, so it's going down, which means this needs to be negative. Okay, and the math doesn't show us that because we had a square root. So this is when we have to recognize, is it going up or is it going down? If it's going down, we've got to put that negative into our velocity. Okay, because our momentum's got to be going in the downward direction also. All right, so now we have our velocity and we have our mass, so we can solve for momentum. Okay, we solve for momentum using P equals mass times velocity. So we'll take P equals 4.3 times negative 7.7.
-33.1.
I'm running out of room here. Okay, so our momentum equals negative 33.1, and our units are,
Kilogram times meters per second.
yep, perfect. Okay, try this one on your own. Make sure you make your list. Find out what equation you think you need to use. Okay, do we agree if we're done?
Yes.
Okay, if you're not done, that's okay. So if you were stuck, what happened in this problem is that we took force times delta T equals mass times delta V. Okay, that's all we did. Plugged in those things and solved for mass. Our final velocity was 1.29 because it said it accelerated from rest.